Hello. Hi, everyone. Uh, buongiorno? No, buongiorno? Yeah, okay, buongiorno. Um, Thanks a lot for coming to this talk on principles and patterns for streaming data analysis. My name is Galder. I'm an engineer at Red Hat. I originally joined JBoss in 2006, and I actually moved to Switzerland. I was living in Neuchâtel for a little bit. And then quickly, obviously, Red Hat came and acquired JBoss, so I became a Red Hat employee. I primarily work on a project called Infinispan, which is an in-memory key-value store, which I co-founded in 2008. I kind of have two roles. I am a little bit like community lead, so I go out and talk to a lot of people in conferences, and I get a community feedback channeled internally as well. But I'm also a core developer. I've been over 10 years. I've worked in all the parts of the code base. And these days I work a lot on the Openshift integration. I don't do this job alone. I do pair programming with someone called Otis. He's listening to this presentation, and he might have a comment or two to make, because really the star is him. I know nothing. So the data is overwhelming us. The amount of data that is being generated, whether it is by web applications, people, smartphones, IoT devices, is brutal. It's going to get bigger as we more parts of our life get automatized, whether it's via more devices, more things we do, more things we track, etc. So there is all this data that is being generated out there that we have the need to understand what it means, what it does. And one of the key challenges about this data is that you can pile it up and then run some processes, etc., over time to see what's happened. But there is a lot of cases where you just want to find out what is going on right away, maybe because finding out what's going on right now is the difference between maybe keeping or losing a customer, or it's the difference between making money or losing a lot of money. So how do we process all this type of data in a streaming way? What I want to propose to you today is an architecture based around this layout, where we've got obviously data coming in into our system, and we've got different components that are going to help us kind of build a streaming architecture, and we're going to be studying them a little bit throughout this talk, and then at the end I'll show you a demonstration of this architecture that I'll run it on my own environment. The first part is the one that we call the collection tier. Here's our entry point into the system where data comes through. Independent of the protocol that we used, whether it's HTTP, TCP, or whatever, there are kind of a number of patterns, interaction patterns that are used today. The most basic one is the request-response pattern, where you've got a client or a service that makes a request to a server and expects a response. This kind of interaction pattern, in the past, we would have been used to having like a synchronous type of pattern when a client makes a request and it blocks until it gets a response. Given the scale that we have these days, and even our patience to wait for things, this doesn't fly anymore. It's any type of request-response patterns have to follow a non-blocking asynchronous communication pattern. And you see throughout all the layers that we have, this is the pattern that you need to be promoting, because any blocking that happens basically ends up becoming a snowball effect. So it is a much more efficient way to basically make a request, do something else, and then when the response comes, react to it, basically. In the demos as well, I'll be using all the time this kind of interaction patterns. A kind of a similar pattern to request response is request acknowledgement, right? Where you make a request, but all you want to know is an acknowledgement. And you might say, well, that doesn't happen very often, but actually that happens on a daily basis. Whenever you go online and make a purchase, what do? You make a purchase and you get a confirmation number. The moment you've got the confirmation number, that's it, you're happy. You don't need to worry about whether there's going to be enough stock. You trust the guy will have enough stock. They will have someone to take the piece of what you purchase, sending over to you, etc. So this is quite common as well, but it's just a subset of client request response. A different type of setup is when you've got this kind of message broker in the middle. So you've got these logical topics that interact with n number of devices or autonomous vehicles or whatever that feed in data into a particular topic, and then you react to it based on areas, etc. So this is another pattern that is very common. Another common pattern you might find is what we call fire and forget, where you've got an incoming service that sends a request, but it doesn't need a response. This might happen when you have systems where the client or the origin doesn't need to process the response itself. So, for example, if you are in a data center and you have servers that are sending CPU or memory usage to a backend kind of monitoring server, for example, they don't need the response because they're not the ones that are going to react to what they're doing in the memory themselves. Another pattern that is quite common is what we call the stream pattern, where you say you make a request to a particular service, and then once you connect to it, you establish a connection, and then from there you start getting kind of a streamed responses. That's very, you'll see this when if you're trying to analyze a Twitter stream, right? You connect to the stream, then you start consuming the streams, and then you react to it. So this is a little bit quickly explained a little bit some of the patterns you might find when it comes to collecting data. Once you've got your data, so it's coming in, what do you do with it? It often makes sense to have like some kind of buffer or kind of like a way to decouple your data coming in from your analysis data. That is because often you'll be feeding in data into your system, but then your analysis might take more time to consume compared to the speed of the data that is coming in. So obviously you need to somehow decouple these two parts in order to give them a little bit of buffer or back pressure, right? In order not to pile up the things against each other. Why is this the case? Analysis often requires maybe more processing intensive, so obviously it can be faster than just reading data, parsing it, and pushing it to the next layer. Or you might have situations where the analysis tier is not responding, is not analyzing things immediately. So you might do it in batches, right? It might take hourly data, analyze that, or maybe daily, etc. Normally, for a streaming architecture, you normally want to do it in real time. Having this message queuing system normally requires you to have some kind of durability to your messages. So that means that you need to give it some kind of fault tolerance, disaster recovery, and that by itself also allows you to do offline consumption. In this area, there are loads of different tools out there. Like if you think Kafka, Stramza, there's a lot of like different tools that can help you with this kind of messaging. Something that's important about the message queuing tiers that they normally provide you some kind of guarantees about the delivery of things. So they, in the worst case, they say it is at most once delivered. So that means messages might be delivered or not. Some of them might get lost, which normally is not used a lot. Then you've got the at least once when messages are not lost, but a message might be processed multiple times in case of failure scenario. And you also got a delivery semantic, which is exactly once, where messages are not lost, and it's only commuted once and once only. So my pair programming buddy Otis is calling bullshit at this point. It's like saying, you're actually lying, Galder. You've no idea. I've got a lot of experience with these systems, and that doesn't fly. Exactly once delivery is probably one of the most, it's a very misleading term, or depending on how you look at it, it's an outright lie. That is because when you want to do exactly once delivery, you need to think about what are you talking about? Are you talking about guaranteed delivery or guaranteed processing of the delivered message? And that's very, very difficult because you might say, okay, I've delivered my message to a subscriber, but didn't manage to process it. It might have crashed, so you don't know whether it's actually processed it. So the only way for you to guarantee that a message has been delivered and it's been processed is to actually have application awareness and collaboration between the different parts. So this means that whoever is subscribing to a message has to be able to say, hey, have I processed this message? If I have processed this message, up to which point have I processed it? So what happens is that any attempt to do exactly once delivery really means that you've been able to figure out a way to figure out for duplicate, or which part of the previous request you've already done. So that means you are back to at least once. And on top of that, you're incurring the extra cost of a consumer having to tell the publisher that I've actually I've actually processed that message. So in essence, exactly once is at least once, but with extra cost. Okay, so this is something that is important to understand in this kind of messaging queuing tiers. So we've got our data through the initial collection tier. We then kind of buffered it into a message queuing tier with some durability, and now we start like passing it into our analysis tier. The analysis tier here, we're trying to do normally in-flight analysis. So data, we kind of thinking about data always being in motion, and then we kind of like pushing it through our analysis tier as quickly as possible so that we can react to it. In a non-streaming system, for example, if you go to a traditional database, what you do is you have data in your database, and then you do queries to get answers when you need. Here, we're doing the opposite. We have got a query, and then we push the data through it. So that means that whenever new data gets fed into the system that matches that query, we kind of send it in the other side. We kind of push it out. Okay, and how do we do this? This is quite commonly done with something that we call continuous query, where the idea is you build a query and then you attach normally some kind of listener to say, if new data that matches this query gets published into our streaming, into our query, then react to it. Or maybe if data stops being part of the query, right? So maybe the query had a subset and data is now no longer part of it. So maybe you want to do something. Here we see a lot of use cases in real life. For example, if you're trying to track someone's behavior, a person's behavior through a website, you see they're clicking things, they're kind of browsing different products. Based on that, you could decide to show them some advertisement or not. If you're trying to react to traffic issues that are happening in a particular area, so you kind of create a query for each person based on their area, and as things are happening in that particular area, then they find out. And even in the finance sector, if you're trying to react to fraud detection, right? So you want to be able to detect certain patterns and react to them immediately. Things like continuous queries are often combined with time constraints. So for example, if you're trying to think about traffic, for example, in a particular area, you're normally interested about traffic in the last hour, maybe, and you're not interested in traffic, what's been happening in traffic for the last 7 days, for example, right? So you often see these kind of continuous queries being combined with time constraints. This is a short part of what you can do at the analysis layer. There's many other topics you could discuss, for example, like summarization. How do you do, what kind of techniques you use? Here I'm trying to make it a little bit more focused on some of the topics that I'm going to be demoing. But if you want to find out more, then I have some sources for you as well. Finally, so we've gone through our data, and then it's quite common once you've analyzed it to store it in some kind of in-memory data store. This particular piece, I'm going to be skipping it because I'm going to be talking about it in the end. But essentially, it just gives you a temporary place for you to then react to that data. And finally, what we end up here is a data access tier, which can offer patterns very similar to those in the collection tier. But what it is more interesting here tends to be the kind of protocols that are used for pushing data out there. there are primarily four type of protocols that are used these days, generally. The oldest one probably would be webhooks, where you basically is a kind of a conceptual HTTP callback that allows you to link different service around. And one of the classic examples here is GitHub, right? Back in the day, when you wanted to create a commit and then do a CI build, what you would do is you create a webhook between your CI and your GitHub repository, so that whenever you did a push, then you would kick off a CI build. Normally, these days, it's used for frequency of messages that are fairly low, so it's not often used in these scenarios. Then we've got HTTP long polling. HTTP long polling became quite popular back in 10, 15 years ago, when people started to do Ajax, when they would have clients establish a connection, keep that connection open, and then use that connection to send data to the clients. But the HTTP long polling tend to be quite finicky, and it used to be quite inefficient because sometimes clients would basically open and close immediately, or maybe they wouldn't work very well with mobile devices, where devices would go into sleep, etc. And as a result of that, server-side events were created, where they were trying to improve on the things that were done with HTTP polling, and it allows you to do, in a standard way, push messages to connected clients, but it also enables you also to create work with fault tolerance. So that means that you can actually build into your application a way to detect whether those messages were delivered to clients or not. And further evolution of server-side oops, what did I do? Did I come out? Server-side events would be WebSockets. WebSockets is mostly an improvement of server-side events where it works both directions, not only from server to client, client to server as well, and it's also a more efficient way of doing server-sent events, because when you use WebSockets, the initial handshake goes over HTTP, but afterwards it gets upgraded to a TCP connection, so you don't have all the extra work you have to do to deal with HTTP. So far so good? Okay. So what I've done as well is I've gone and tried to make an applied version of this architecture with technologies that I'm familiar with and technologies that I regularly work on. The first technology that I wanted to quickly mention is Openshift. How many of you know Openshift? How many of you know Kubernetes? Okay, a few more. Well, essentially, Openshift is a Kubernetes distribution with extras. So it's a Red Hat Kubernetes distribution which allows you to run, to kind of develop, host, and scale applications in private environments like your own companies, or in a public environment as well. It's multi-language, so it is not just Java. You can build applications in Node.js, PHP, etc. And what is important to understand is that OpenShift is essentially Kubernetes. So most of the things that you can do with Kubernetes, you can do with OpenShift, and sometimes we've added a few different kind of extras on top of it. Then the next step is we're going to be using something called Vertex to kind of we're going to be using it at the end, because it enables us to kind of abstract the collection and the data access tiers. And on top of that, what we are going to do is we're going to combine it with something called RxJava. Essentially, Vertex itself is a toolkit for building reactive applications. So it has a lot of APIs for working with HTTP, with WebSockets, with SockJS, with file-based systems, etc., in a reactive way. So it's always event-driven, non-blocking, which is really, really good for this kind of applications. Why is it so important, apart from obviously of all the blocking and all the impact it can have, is that having event-driven non-blocking applications means your application can scale with very, very small number of threads, and it can handle a lot of requests, a lot of traffic. What Vertex has done is integrate with RxJava. So RxJava is a programming language that allows you to, well, a programming framework that allows you to handle data and event flows and combine them in an easy way. And it's particularly good at event transformation and coordination, which is very, very common in this kind of streaming applications where you've got different sources of events. So what Vertex does is essentially use RxJava in order to kind of give APIs that allows us to push things to HTTP in a reactive way, consume things in an unblocking way, etc. The final bit is going to be Infinispan. Infinispan is going to allow us, our in-memory key value store is going to provide us, obviously, with an in-memory data storage, but on top of that, it has some analysis capabilities within it, and in this particular case, it's also going to act as kind of our intermediate kind of buffer, right, where we put data, we then afterwards store it. I've put a little asterisk here because Infinispan itself is not a messaging product, really. If I was building this in a real environment, probably I'd be using Kafka or similar technologies. But in this case, it just keeps my architecture a little bit simpler. And I work with Infinispan, so it makes it a little bit easier for me to demo. And it makes it a little bit runnable in my laptop. So Infinispan, in essence, what it allows us to do is it's an in-memory key value store that we can access both in library mode. Library mode means from a Java application. So Infinispan itself is written in Java, so if you have a Java application, you can run it embedded within your own application as a kind of your own a little cache, a distributed cache. But we can also talk to it remotely, and we've got clients for it written in Java, C++, C#, Node.js, etc. We've got HTTP RESTful APIs to talk to it, and also we've got like a binary protocol called HotRod that allows us to do a bit more topology, to track topology updates more clearly. This obviously was designed at a time when we didn't have Kubernetes or anything like that. These days, some of those things related to HotRod can be handled by Kubernetes or similar technologies. I don't think you can see it really very well, so I'm a bit disappointed. Some of the things, very important thing, that we can do cross-site replication, so you can actually have distributed clusters of data and then connect them via inter-site communications, which is a very powerful feature. It's probably one of our main features. We've got indexing and querying capabilities, and as we'll see in my demo, we also have continuous queries. So we'll see how those work, and then we've got listeners, distributed execution security. You can actually have persistent in the backend. You can persist the data if you want, management, etc. Obviously, you can run it in any environment, in your own environment, on top of Openshift. And then we've got a lot of integrations with things like EAP, Wildfly, JWS, Fuse, Spring Boot, Vertex, Spark. Obviously, one of the things that Infinispan does, it allows you to have some querying, some indexing. But apart from that, we also integrate with some of the more kind of powerful tools out there for analysis, like Spark or Hadoop. And then we actually, for our indexing, we are powered by Lucene. So we use Lucene behind the scenes for that. So this is kind of like a very quick overview of what Infinispan does. So the demo that I'm going to show you today uses two streams of data, and they come from Swiss websites, and we happen to be in Switzerland, so it's quite fitting. The first part comes from OpenData.ch. They have what they call a transport API. This is an API you can query to get information about public train station state. So we can go and check what is the station board of Basel or Lugano looks like, and it will show you information about the trains. These trains are coming on these platforms, whether they are delayed or not, etc. And then in our demo, we will have each individual entry in a station board. We will have different as a stop, and this is going to be relevant when I come to show you the demo. The other stream of data comes from SBB. This is actually a public API that allows us to see a train's particular location on a map. So what we are going to do is we're going to be combining these two types of information to create two types of applications. So here we've got Openshift, and then we've got here a 3-node Infinispan cluster, so that's going to be where we store the data. Now, what my application has done is we've captured data of, from both streams for about 2 hours, and then we've cached it locally so that we can consume it, and I can show you a demo. In real life, I would be pulling or getting notifications from the APIs themselves. What we are trying to do, what we're going to be doing is we're going to be taking that data about the station boards, we're going to put it into Infinispan, and then we're going to create in a continuous query that is going to give us information about those trains that are delayed. When we get information about those train delays, we're going to be pushing it into a dashboard, a JavaFX dashboard that runs outside of Openshift, and this is going to be going over WebSockets. So we're going to be doing HTTP WebSockets, and that's here we're going to be using a Vertex feature to actually channel things that we put into the Vertex event bus to then those get pushed into WebSockets into our JavaFX application. That's one. Then this data about delay trains, it's also going to be fed to another part of our system that is going to say, hey, not only do I want to know which trains are delayed, but I want to know which positions. So what it's going to do is get that data about delayed trains. It's going to take the data about train positions, which also is going to be fed into our data grid. And then that is going to be pushed into another WebSocket here. And what we're going to do is we're going to have a little Google Maps that shows us the different trains that are delayed. And as they get delayed, we're going to be seeing, as time goes by, accelerated, of course, you're going to see them moving around. Why would we want to do that? Because obviously, in SBB, I'm sure they've got a lot of IoT devices to know where things are going wrong, but maybe you want to know at a bump level where trains are getting delayed. Maybe it's a particular zone that is having an issue. So this is kind of a different use of streaming data. So demo time. Let me switch to displays. We kind of switch to. So in this case, I'm not going to be doing any live coding because I was using the first part of the talk to show you some of the theory behind it. So the application itself is already running. So if I hold on, can I get a better resolution because this sucks. Okay, that's a bit better. Okay, let me see. Okay, so here that you see here, I've got Openshift running locally, and I have 3 main applications running. On one side, I've got my data grid, which is 3 pods. Basically, those are the 3 my Infinispan cluster that is talking to each other. Then what I have is a data grid visualizer. This is a funky tool we created for a keynote demo for Red Hat Summit like 8 years ago or so. And it basically allows us to show like the data grid in a graphic, kind of in a cooler way. So what we have here is the data grid in action. So what I have here at the top, here, I don't know if you can see. Oops. So I have here is a little selectable that allows me to choose which namespace or cache. The one I'm interested in here, I'm going to be the station boards, and that's going to be, we're going to see what happens. So each of these nodes is one of the pods that I was talking about. Then we've got a little counter here that says 0. That's the amount of data that is in each of the nodes. So these caches have, or this namespace of cache has been configured with a number of, or a replication factor of 2. So that means that for each piece of data, we keep 2 copies of the data. So then we use consistent hash-based distribution behind the scenes to kind of keep that data, distribute the data around, and it's designed in such a way that we kind of more or less keep the same amount of data in all the nodes, more or less. It's not exactly the same. So what we're going to be doing is what happens when you start pushing data into the system. And that's the first thing we're going to be doing. Let me see. Profiles, presentation, yeah. Okay. Cool. So there we are. Now, let's see. Just want to get to this one. Okay. So actually, I have this one already, but it doesn't matter. Okay. Now, what do we need to do is how do we start? So as I said, our applications already got some cache data. So what we need to do is start feeding that data into the system. The way we do it is here. Okay, that's from the previous round, I think. Yeah. What we have here is we have our app map project. That's kind of our entry point. So what we need each address. What we're going to do is we're gonna tell it curl. We've got a little HTTP endpoint there. And we call it inject. So what inject does is starts injecting data into our system. So if we go back to here, we should be seeing data to the station. Why are you not? Oops. Data should be appearing here. So basically, we should be getting like some little dots appearing around the nodes. Oh, there they are. But it's just appear a little bit, yeah. So we should have seen them a little bit increasing a little bit more, essentially. But what you see here, you see the number of entries is growing each of the nodes, which is approximately the same. It's just, I think, the little web app we created here. Sometimes it takes a little bit of time. Apart from this, we've got another cache, which is train positions. This one contains information about where the locations of those trains are. It's not reacting very well, but anyway, I'm going to ignore that for a little bit. Now, okay, we're pushing data into our system. What is happening there? I wanted to show you a little bit some of the parts of the code that are powering this. So when I call inject here, that's essentially creating a Vertex route. So this is an HTTP route that allows us to consume data. And when the inject happens, essentially what we're doing, we're starting a couple of verticals. Verticals are like units of processing that Vertex uses. For this first one, we're interested in the station board vertical. What this does on a start, it adds a continuous query, which I'll talk about in a little second. And what it does on top of it, it creates something called inject. The inject, what it does is, basically, we've got a little file that gives us where we've got this data about station boards. And then what we're doing is we are reading it using Rx Java APIs. What that means is that we create a flowable of each of the entries that we see in this file. The flowable is a way for you to subscribe to a kind of an event that returns more than one element. So it means that for each entry that we see, we then map it to a station board kind of entry, and then we store it into our data grid. We do it using with an Rx facade that we have here. Now, the inject itself is pretty simple. The other part that we do as well, we set a continuous query. Here, what we're doing is saying, we create a little query where we say, for each stop, we're interested in those stops where the delay is bigger than 0. So it means that a train is delayed. And what we do with it is we take the Vertex event bus and we publish it into an address called delay trains. So that means that we execute the query, and then whenever we go through the data, we publish into this address, and then as more data gets pushed there, then we add it here. Now, okay, we've got it in the event bus. How does it make it that all the way to the front end? How is that going to go all the way to our JavaFX application? That is happening in the main vertical. Here, what's happening is we got an address called delay trains, and what we're doing is anything we put in the delay trains event bus, we actually push it. We use sock.js to basically push that to via WebSockets to the front end. Obviously, here what we do internally is we say we define different permissions. We say only those messages that get sent to this address are allowed to go into the WebSocket, so that not everything goes in. and that's essentially what we do as well. For ease of use in here, when I demo, what I did is whenever I get a connection from the dashboard, I'm gonna start I'm gonna re-inject the data. So what we need to do next is I need to start a dashboard, which is my JavaFX application that basically is gonna take that data about delayed trains and it's gonna show it. So if I run it now, so that's essentially that's as far as my JavaFX skills go. So what I'm doing here is essentially data is getting pushed in the backend. So if we go back here, and then we go to the station board, we should be able to see data getting republished here. But essentially what is happening as data is getting pushed and some of those trains are delayed, they are appearing in our JavaFX application. And this is the first part of application. So we take one stream of data, we run a continuous query, and we consume it. Now, the second part is next. Now, what we want to do is combine this information about trains, and we want to combine it with the data of train positions. So what we want to do is we want to create a Google Maps of those trains that are delayed. So what we see here is those trains that are delayed are also being mapped through our system. And then what we're getting is these little dots here that show the delays as they are happening. So if you look closer, you see some of them are starting to move. Maybe not around here so much. Yeah, you see this one is kind of moving across. So basically what we're doing is taking each of those information about those trains and we're kind of merging it into our Google Maps application that allows us to track them. We can go to other areas. What I've noticed is there's not many delayed trains around Lugano, which is really good. I think, where are we? Yeah. No dots around there. But if any of you come from Lausanne or Geneva, yeah, this particular section between Lausanne and Geneva is one that gets delayed quite regularly. It's a big engineering project going on to expand it, I think, and then we can see that this is actually why they're doing it, because there's a lot of these little dots that are delayed. So trains do get delayed in Switzerland. It's funny, when I've given this presentation outside of Switzerland, whoops, some of them are flying actually. Why? When I've given this presentation in Switzerland, outside of Switzerland, they have this conception that Swiss trains are never delayed, which mostly they aren't. But obviously we can show them that they are sometimes. And this is more or less what I had to show you today. I hope you learned something. I know it's a big whirlwind of information here. Finally, I wanted to just leave you with some of the URLs. This application that you see here is available publicly. It's a demo application we have in this GitHub repository. I have some, what I've been doing today, the instructions to do that, I've got them there. If you want to try it locally, you can, because you can run it on top of, like me, on top of Openshift running locally. I've been using Minishift, for those that maybe want to know. If you want to find out more about Infinispan itself, obviously go to infinispan.org. We also got a product version, which is called DataGrid, and that's obviously has got multi-year support, etc. And then Openshift and Vertex.io, you can find more about here. I forgot to add, also when I post this online, I'll add some links to find out more about the streaming data architectures and in general. I forgot to do that. That's all I had to talk about. I've got about 10 minutes for, yeah, that's it. Any questions?
Is there a pattern for streaming something like fork join to have an event travel different paths and then rejoin him?
Any pattern for that? Normally for that kind of coordination. What you can often do, you mean for Java, or you mean just in general as a pattern?
in general, if you want to parallelize this processing and then join it?
Normally, when you use at the Java level, for example, if you're using Rx Java completable, or you use the standard completable features, you can span different processes in parallel and then kind of join them together at the end. When you are using something like if you're using, you can also do with Spark. Sometimes you can do SQLs, like different, like you can do like. Well, that's more like no. That's more for processes. Here on processes, what we can also do is you can do stream executions as well. Java Streams API. We've extended it so that you can run it on a distributed environment. So there you can also do these kind of things where you, if you want to do map through the data or do map filtering functions, then we can send them to different nodes, and then they get brought back and put together. So that's normally more about a framework level thing. So it depends what framework you're using and what capabilities they have, I think.
Can you repeat the name of this?
It depends on the frameworks themselves. Normally about if you're doing Hadoop jobs or Spark jobs, basically they allow you to kind of split your data based on certain parameters and then bring them back together. If you're using directly Infinispan, normally we use consistent hash distribution to separate the data ourselves, so it's a bit transparent. So it depends a little bit what also depends on how you shard your data, whether you shard it yourself or whether the framework itself does it for you.
Thanks.
Other questions? I guess we are full.
Thank you.
Thank you.
Thanks.